So assuming we have a surface area of 8 square inches, we're going to maximize the volume of an open top box that's rectangular in shape that has a square base. So we need two things. We need the objective function, the one we're trying to optimize, so v equals x squared, because that's the base h. So if we draw a picture of our box, because it has a square base, we know that those dimensions are going to be the same, so x by h. And the surface area, which we know is 8, this is our constraint equation. Well, we've got a bottom there that's got an area of x squared. And notice each of the sides are going to be x by h. And there's 4 of them, so plus 4xh. Now what we're going to do is we're going to use our constraint equation to get our objective function in terms of one variable. So we're going to solve this for h, which will be 8 minus x squared over 4x equals h. So that's just solving that one for h. And I'm going to plug it into my h here. So I get v equals x squared times 8 minus x squared over 4x. Now we need to simplify, and we can cancel an x out between those two. And I'm going to rewrite this. I'm going to pull the 1/4 out front and now distribute that x to the remaining terms. So times 8x minus x cubed. So there is the function I'm trying to maximize, and we do that by taking the derivative. So let's just call it v prime, which is 1/4. Derivative of 8x is 8 minus 3x squared, and we take that derivative and we set it to 0. Now this part here will never be 0, so I set that to 0 and I solve. 8 minus 3x squared equals 0. Solving, I get 8 equals 3x squared, and I'm going to, as you can see, I'm going to divide both sides by 3, and then I'm going to take the square root. I'm not worried about the negative because I can't get a negative side for this box. Now let's confirm that this will give us a maximum. One nice way is the second derivative test. So I get 1/4 negative 6x. If I were to plug that in, I'm going to get a negative number, which means, remember, concave down, which tells me my critical point sits at a maximum. So this value x, these bases here, are going to be square root of 8/3 inches. Now we were asked to find the volume, which means we need to find h. Here's h in terms of x right here. So h is going to be 8 minus square root of 8/3 squared all over 4 times square root of 8/3. It's a little bit messy, but we can simplify this up a little bit. We have 8 minus 8/3 in the numerator over 4 times square root of 8/3. Let's see how much simplifying we can do here. This is the same thing as 24/3. Excuse me. So 24 minus 8 gives us 16/3 on top over 4 times square root of 8/3. Now, this is the same thing as 1/4, or excuse me, 4/1, so we could flip that and multiply the 1/4 here, and that's going to make that a 4/3. So we have 4/3 over square root of 8/3, which we do want to simplify up a little bit. So let's see what happens when we do that. Well, dividing by a fraction, you can multiply by the reciprocal, so we get 4/3 times the square root of 3/8, which I know looks kind of weird, but what we'll do is we'll put this all under the radical. Now, to put those under the radical, we need to square them, so we have 16/9 times 3/8. So now we can do some canceling. And we get that h is square root of 2/3 inches. We can now find our maximum volume. Let's just write it here at the bottom. Our maximum volume is square root of 8/3 times square root of 8/3 times square root of 2/3. And without worrying about radicals too much, we can just do all this under the radical. 8 times 8 is 64, times 2 is 128. 3 times 3 times 3 is 27. Square root of that. Yeah, we could pull out some perfect squares, but for our purposes we do have our maximum volume.